Hi, and welcome back to Allen High School. We are in the midst of talking about structure and function issues with mixtures. Now, for those of you who are just joining us, this section or this unit is not covering the mathematics of mixtures. We've already discussed molarity and the ways of describing concentration, and we've already discussed colligative properties as an introductory review unit. So this is focusing mainly on the structure and function and properties. And this is a newer section. We talked about metallic, and now we're going to do our network covalent, and then we'll talk about ionic and molecular covalent. So one of the issues with mixtures for network covalent is something called doping. In the semiconductor industry, they typically use for this wafer upon which they will build numerous little circuits, hundreds and hundreds of little computer chips, and each of those computer chip contains thousands upon thousands, I don't even know how many thousands now, of circuits. Okay, and that would be on what they call a wafer. That's about the size of a tombstone pizza, that circular wafer. I tried to show it as an ellipse from the side, but that'd be a circular wafer. So now, when the wafer starts out, it's relatively thick, and it's made, this is the wafer, it's made of silicon. And believe it or not, they make it from sand. Whoa, time. I bet I have time. If I can find that, I have an old VCR, an old videotape that shows how computer chips are made, and it's pretty interesting. And that's what it would show, is the way that they make that silicon wafer. And it's a crystalline structure, and that's because of this ongoing covalent, right? Sharing of electrons, but it's not a singular molecule, a discrete molecule with a beginning of the and an end. It's that ongoing network. So this is one of the network covalents that you're expected to know. Now, this is a metalloid, and what the scientists want to do is to be able to control the conductivity, to be able to have effectively, it's called it's an on-off switch. Computer language has a 1 and a 0. And so we have these electrical gates, and I am simplifying to the max here, but they have these electrical gates that they want to turn on and off. And so we want to be able to control the conductivity of segments of this silicon. And so what we do, its conductivity does increase with temperature, but we don't want to have to control the temperature. We want to control it by changing its structure. And we call it doping. Scientists call it doping, and I never quite got this idea, but had to just accept it. We typically think of an impurity as an undesirable thing, but in this case, this is an impurity that is desired, and it's put in there to help control the conductivity of the material. Now, there's two types of dopants, two categories of dopants. One is called a p-type. The P stands for a positive charge carrier, and this one is very abstract. I'm going to try to explain it now, but I'm also going to do something with the smartboard where I can move things around more effectively than on the Mimeo. I probably could have figured out a way on the Mimeo, but it's a lot easier for us to see it on the smartboard. That way you can manipulate it too. Now, it's really electrons that are moving. All right, it truly is the movement of electrons. That's what conductivity is. But there's an appearance, it appears as if gaps, or what they call holes, are moving. Now, in a p-type dopant, boron is typically used. These are gases. This is actually the type of gas that my husband's facilities work with. And we'll use boron. Now, silicon has 4 valence electrons, right? So each silicon had 4 valence electrons to start with, and then the other silicon bonded, and so that's its 4 valence electrons. Okay, and then the next silicon came in, and it had 4 valence electrons, and on and on and on. So silicon has 4 valence electrons, which provides that complete structure, much like carbon and diamond. You can think of that as an analogy. But boron has only 3 valence electrons. All right, so let's look at the picture, and I hope that this statement will make more sense when we see the picture. So what we have here is if in place of a silicon we pop in a boron, boron only had 3 valence electrons. So that leaves a gap or a hole in the bonding structure that's missing an electron. And so I just showed 2 of them here for the sake of demonstrating it. So instead of having the 4 that normally surround, it's got these holes or gaps because boron is, you could think of it as being electron deficient in terms of this structure. Okay? So hopefully that makes sense. Now, here's what happens. If an electron shifts location, all right, so we have our hole here. If this electron, let me see if I can get us some more room here. Let's look at this electron. If this electron shifts and hops into that free seat or that free spot, now what's going to happen is the hole has shifted. The electron is moved, but the hole has shifted over to the left. And so if we take a look here, I just grabbed that electron. If that electron hops over into that gap or that hole left behind, that leaves this spot deficient of an electron. So do you notice that it appeared that the hole moved? Okay, and so it is the movement of holes. I know that seems really weird, and that's why we call it a positive charge carrier, because it's that deficiency of electrons that appears to be shifting, in this case to the left. Okay, so it was here, right? Come right down, and it shifted over to the left. This hole was here, and when the electron hopped into it, it shifted it, so the gap was to the left. All right? I think this is hard and somewhat abstract. So ask me lots and lots and lots of questions, and I'll do everything I can to explain and re-explain. Now, the other type that you need to know about is an N type. N stands for negative charge carrier. This time what's going to happen is we're going to have extra valence electrons, and 2 substances that can provide that are arsenic and phosphorus. Again, silicon has the 4 valence electrons. Well, phosphorus has 5 valence electrons. So if we pluck out a silicon and pop in a phosphorus, 4 of those electrons will fill in the bonding structure. Okay, and that leaves that 5th electron free to move. It's not tied up in the bonding structure anywhere. So here's another phosphorus. 4 valence electrons are used, so you can kind of circle that. Do you see those are used to fill in the octet? And then the 5th is free to move. So once we have those extra electrons in there, if we have freely moving electrons, we have conductivity. So that's why we can control the conductivity, and they can control the amount by controlling how much phosphorus is doped into the silicon. Okay, so that's how we get mixtures with a network covalent, and how changing that structure alters. In this case, we're focusing on the conductivity as our function. So all right, that's network covalent. We're going to move on in the next video to discussing ionic and molecular covalent. Until then, this is signing off.